Thank you so much for being here today. We're going to talk about pendulum swings and models and metaphors. So, you know, a pendulum is very simple. It just goes back and forth like this, and we can watch it go back and forth. I can try to hypnotize you to believe in pendulum, but that's not the purpose. But the pendulum actually goes back very far in history. So over here we have three pendulum. They're swings. One is from 2,000 years ago. It's an artifact of a clay figure, somebody on a swing. Then you have, of course, Krishna on his swing. And then the third picture is from the 19th century. And I just wanted to focus on that one for a moment, because you have the beauty of the person, the attractive person going back and forth on the swing. But then the man is not attending to the beauty. He's looking at he's analyzing the pendulum in the sand on the ground. And I thought, is he missing the beauty when he's trying to do the analysis? And so I realized that the theme for today should be, how do we combine the analysis with the beauty? How do we do physics analysis without losing the beauty of the pendulum? And how can the analysis maybe enhance the beauty as well? So I need to know from you how much you know about pendulum, so I know where we're going on this. So if you can show me with your fingers, a 1, meaning you have very little familiarity with the pendulum. 2, I know something, but I've never really completed a laboratory experiment. 3, I advise I and or my students have done a lab. And 4, I know everything there is to know about pendulum. So let me see with your fingers. I see a 3, a 2, a lot of 3s, a 1. Thank you. Okay, so you have to vote. You have to vote. 1, 2, 3, 4. Thank you. Okay. Yeah. So good. So we're really all over the map. So let me just tell you about a pendulum. It's really very simple. If I take a pendulum and I swing it, we call the time it takes to go back and forth the period. So I just tell you that because if I forget to call it the time, I say the period, it's the same thing. The time to go back and forth is the period. And the question is, what variables could affect the swing of this pendulum? And what could we change? Well, you can see that we could change the length. So if we change the length, 1, 2, 3, 4. Well, if I change the length like this, it's now 1, 2, 3, 4, 5, 6. So the length certainly affects it. But how much the mass is at the bottom, does that affect it? How much I pull it back, does that affect it? Does the color of the string affect it? Now, I love when you laugh at that. You're so certain of the physics that the color could not possibly matter. Could the mass of the string matter? If I use a very thin string, could that? So this is what we want to explore when we study pendula. And you know, we can change these things that I showed you, and we can do these experiments. They're very easy experiments to do. And let me show you the way it's traditionally done in the schools. What they do is they tell the students that we're going to take a pendulum of 10 centimeters, then 20, then 30, then 40, and you're going to measure the time it takes to go back and forth. You'll have it swing 10 times or 20 times. And you'll get these, and you'll make a chart. And the students make the chart. And there's something right about this experiment. It's very good. The students take careful measurements. They learn how to take careful measurements. They learn how to make a graph. So there are less things they learn about pendulum. But there's so much wrong with this approach. So much. With this approach, there's no interest. There's no motivation. There's no tension. There's no drama. Why are you measuring the period of a pendulum? My teacher told me to. And my parents told me if I do well in school, life will be good. But we need more. So I don't know if you've seen these movies. How many people have seen RRR? How many people have seen RRR? Not everybody. Oh, Wizard of Oz? Different people. And what is it? Oh, E.T.? Okay, so if you've seen one of these movies, but it can be any movie, if you think about the movie, there's tension in the movie. There's something going on. Is Ram in RRR a good person or a bad person at the beginning? What's going to happen? Is he going to live? Is he going to? Who's going to live? Who's going to die? You know, what's going to happen to the British? The Wizard of Oz, will Dorothy find her way home? E.T., will E.T. find his way home? So this is why we watch movies, because there's drama and suspense and interest. Even when we know the ending. So how many people have seen Titanic? Everybody. So everybody's seen Titanic. Why do you go to Titanic? We know how it ends. The boat goes down. We know, this is not a surprise for anybody. So how, when you know the ending, do people instill suspense and drama and interest? And they do it by having other plots, like will she find, who's going to live? Is Kate Winslet going to live? Is Leonardo DiCaprio? What happens to the jewel? What happens to the, class, cultural disparities is there as well. And Kate Winslet and Leonardo DiCaprio are good to look at. So that's another part in their favor. Now, we have an experiment, gravity. We have to teach students about gravity. And when we teach them about gravity, we say, watch this. If I let it go, it's going to fall down. And they say, we knew that. And the question is, how can you create suspense when it's something that everybody knows? We want to teach students that things fall are interesting. So if anybody who's had a small child about 2 years old or is babysat or whatever, there's a game they love to play. When they're eating at their little table, you put this on the table and they knock it to the ground. And then you pick it up and you put it back and they knock it to the ground again. Then you pick it up and you put it back and they knock it to the ground again. And you will tire of this game before they will. They love that game. And of course we don't know why they love the game, because they can't speak yet. Do they love the game because, how is it going? I see when you lift it, there's a hand there, but when it goes down, what's pulling it down? I can't see anything. Or is it just that I'm controlling a big adult and this is a thrill for me? So here's what I like to do with gravity. I tell students, imagine if I could do the following trick. I take this and I let it go and it goes shooting over to the wall. Horizontal, just shooting over to the wall. And then I go to the wall and I say, do you want to see that again? And I go, yes, do that again. And I let it go and go shooting to the wall again. And I'd say, that's not, no, one more time, just do it one more time. And you would want to see it over and over and over again. Because you say, how does this happen? And that's kind of trying to remember the mystery of gravity. So when we have something as simple as a swing, we want to do the same thing. Now, a colleague of mine once said, if mystery books were written the way a physics text were written, the first 800 pages would be legal penal code, and then you would find the body behind the couch. Right? Because you go through chapter 1, chapter 2, chapter 3, and it's like, let me tell you this, let me tell you. And then maybe at the end of the semester in the last class, there are some puzzles where the physics people are working on that are kind of interesting. 800 pages of penal code, then you find the body behind the couch. That's not the way they write mystery books. We shouldn't write physics books that way either. We want to have the tension, the puzzle, and the drama. So here's Galileo. Galileo, the story goes, was in church, bored or whatever, and the chandelier was moving back and forth ever so slightly. And he decided to observe that pendulum moving back and forth. And when he did that, he noticed that the time, stayed the same. It went back and forth like this. It stayed the same. And so for Galileo, those observations that he made, in his mind, the chandelier became a pendulum, and then the pendulum became a clock. They didn't have clocks. So the question we ask is, why didn't Aristotle do this? Because Aristotle as well also studied pendulum. And Aristotle was a brilliant mind. Why did he not make these same conclusions as Galileo? Well, it's probably because the period is not perfect. And Aristotle probably saw that and said there's no rule about that. What Galileo did, though, was he said, in the perfect pendulum, in my mind, it would be exactly the same. So Galileo says, let me tell you the way the world should be, not the way it really is. And it was those kind of insights that allowed science to progress. So here's an example of that. So Galileo decided to take, let me see, there it is. Okay, so Galileo is going to build a ramp. And he's going to roll a ball down the ramp. And when he rolls the ball down the ramp, he wants to observe what happens to the ball. So he notices that when he rolls the ball down the ramp, the ball will start going down the ramp. And as it goes down, it'll go, and we know it's going to go down to the bottom, but we also know that it's going to go up to the other side. How high does the ball go? How far up does it go? And in Galileo's perfect world, it goes to exactly the same height. Exactly the same height. And so when he has that coming to exactly the same height, he says, this is a very interesting phenomenon. And so what he then does is he says, I'm going to change the ramp. So he draws another, he constructs another ramp, and he has the ball go down. But this time, the other ramp is longer on that side. And he rolls the ball, and he says, how high will the ball go now? How far will the ball go now? And what he finds is that the ball goes, again, to the same height as he measures. But to get to the same height, it goes much further. So this is a good thing. Let's do the experiment one more time. So he builds his ramp again, but this time when he builds the ramp, the second side of the ramp will be much longer, much less steep. And once again, the ball will roll down the ramp, and Galileo wants to know how high it will go. And once again, as you can guess, it will go to the same height and much further along. Much further distance. Now, those were all nice experiments. Galileo's genius is because of the next experiment. Once again, he makes his ramp. But this time, when he makes the ramp, the second side of the ramp is not at a small angle. The second side of the ramp is horizontal. And so the ball goes down that, and now he asks the question, how far will the ball go? How high will the ball go? And Galileo says, the ball should reach its original height. It will keep traveling forever because it never reaches the original height. So a ball in motion will stay in motion forever, which is not our world. We know that anything we take and we roll, it stops. But Galileo said, no, that's not the way it works. It's not that a rolling ball stops. A rolling ball goes forever unless something stops it. And that way of looking at the world changed the history of science. So here's Galileo, the pendulum becomes a clock, and we have to make this interesting for students. So one way to do it is with some inquiry. So we try to ask students what's going on. So here's the way to do it. I have some pendulum here, and I give one student this pendulum, and I give another student this pendulum, and I give another student this pendulum. And they all come up, 5 students, or everybody in the class has their own pendulum, and I have them swing it back and forth, and I time it for 20 seconds. And I say, okay, count how many times it goes back and forth in 20 seconds. And then you ask them, and one student said, mine went 6 times. Mine went 9 times. Mine only went twice. And you say, why do we get different answers? And the students say, well, because they're different lengths, but they're also different masses. And also some people pulled it back further. So I then say, oh, okay, I have a pendulum in my pocket. I don't know, I'm not going to tell you what its length is. I'm not going to tell you what its mass is. But by the end of today, I'm going to take it out, tell you its length, tell you its mass, and you're going to tell me how much time it takes to go back and forth. Do the experiment, figure it out. And so now there's a little bit of a puzzle, a little bit of intrigue, a little bit of trying to figure out how to do this. And that's one way to make it interesting. There's another way. So this is a book, Longitude by Davis Sobel, a wonderful little volume. And the thorniest scientific problem of the 18th century was how to determine longitude. Many thousands of lives had been lost at sea over the centuries due to the inability to determine an east-west position. This is the engrossing story of the clockmaker John Longitude Harrison, who solved the problem that Newton and Galileo had failed to conquer, yet claimed only half the reward. You tell the students, today in class, we're going to do this. And some students are motivated because they say, I'm going to learn something that saved thousands of people's lives. That's wonderful, that's all. I want to be able to do that. Other students are saying, wait, I'm going to learn something that could have won me 10 crore rupees. And then other students are saying, wait, why did he only get half the prize? And that's going to motivate them. So that's 3 motivations. In a class of 30, we need more than that. But we make an attempt to motivate more students. So the idea is that we need a clock, we need a pendulum clock, so build a clock that takes 1 second to go back and forth. Good luck. Here's some string, here's some mass, go do it. Now, of course, when they do it, some students are more sophisticated than others, so you can have them make a graph of this, and that graph, it's a curve, so you're not exactly sure how it looks. So there's a way that we can change curves into straight lines by graphing the square root of the length versus the period, and then you get a straight line. And straight lines, we know, if they're straight, our eye can tell us that, while the other part, curves, are a little hard to say, is that part of an ellipse, part of a circle, but straight lines, we do that. And then we find that out. But we need more differentiated instruction because we need to ask the question now of our best students, our highest achieving students. And the question for them is, here's a pendulum which leaks. Now, it's a tub of water attached to a string, so it's going to go back and forth. But the water is going to leak out. Now, I don't want you to worry about any, for those physics people here, momentum effects, impulse from the water going out. So imagine this. The pendulum goes back. Here, we dump out some water. It goes back. We dump out some water. We go back. As the water level decreases, I need to know, does the time to go back and forth increase, stay the same, or decrease? Let's see. You all have to vote. Increase, stay the same, or decrease the time to go back and forth. Let me see thumbs. Thumbs. The whole first row here is not voting. I need to. Yeah, you have to vote. Just that you can. It's easy. Just one of these 3 things. Just vote. Vote.
It's complicated.
It's
not just mass. It's also.
No. Yeah, we'll get to that in a minute. But I want to see everybody vote. You know, you're. Why is he insisting we vote? Well, this has nothing to do with pendula. It has to do with teaching. When I ask you a question, I want to know what you think. So I need you to answer. And if you don't answer, and you were my student, I am giving you permission to disengage and not participate anytime you want during the year. Not a good idea. So let's try it one more time. Does the period of the pendulum increase, stay the same, or decrease? So I see a few saying it increases, most saying it stays the same, and most saying it decreases, because you learned that the mass doesn't matter. The mass of the pendulum doesn't matter. If it has 3 masses or 1 mass, it doesn't matter. Only the length determines this. So you would think that's a good answer. It is. It's the right answer. But increase is also the right answer, and decrease is the right answer. Because I differentiate my instruction. I have different expectations for all of you. So let me explain. When the water goes out, we never talked about how do you measure the mass of a pendulum. So you measure the mass of a pendulum from the top of the pendulum to the center of the mass, which is about where this little repair tape is. When the water leaks out, the center of this goes down, so the effective length of the pendulum goes longer. And therefore, the pendulum will slow down. But when all the water leaks out, the center of mass goes back up to this part, and so the pendulum speeds up again. And here's a graph for those who want to see the graph. The red line is not a straight line. It just might appear straight from the image. So let's take a look at, we now know different length pendulum behave differently. So let's take a look and see if we can make this into art. So here we have different lengths pendulum. Short one, longer one. We know the short one's going to go back and forth fast, and the long one's going to go back and forth slowly. So with this apparatus, we're going to be able to look at it head on, and we'll pull them all back a certain amount with the wood, and then we'll let it go and see what we observe. Our eyes love to see patterns. We need those patterns. We must have those patterns. And then it goes back to the beginning again, and will repeat. So, beauty of the pendulum, analysis of the pendulum, they can be one. So I was thinking about this, and there's a book, a child's book called The Dot and the Line, a wonderful book. And it's a story about a dot and a line. And the line is in love with the dot. But the dot is interested in some squiggle and thinks the line has no character at all. And so the line is despondent and very upset, and his friends are saying, "What's happening? You're getting thin. Don't do this. Forget her. Forget the dot. Forget the dot." But the line is so determined. And then one day the line realizes, I can bend. And then I can bend many times. And then if I bend many times, I can get shapes like that. This might impress the dot. And then, even further, I can make curves if I bend infinite amounts like that. I can be dazzling, and the dot, you can see, is impressed. I can be mysterious. I can be complex. I can be profound. I can be compelling. And so the dot now falls in love with the line and says the squiggle is so nothing. The squiggle can't do anything special. So let's look at our pendulum. Here's an early pendulum, 1st century China. It was for earthquake detection. There was a ball inside. If the earthquake went in a certain direction, the different balls would fall and go into the frog's mouth, and they could determine which direction was the earthquake. 1st century, 2,000 years ago. Now, let's see what else we can do with that simple pendulum. Well, we can measure the acceleration due to gravity. You see, the problem was we'd like to know how fast something falls, But if I take my stopwatch, it falls too quickly. I can't get measurements. So the pendulum's going to help us out. The pendulum's going to help us get better measurements. You see, we're going to drop the ball. It's going to hit the ground. That's going to make a sound. We're going to take a pendulum and let it go. It's going to hit the wall. If the pendulum hits the wall before the ball hits the ground, I'll lengthen the pendulum and I'll pull it back and I'll do it again. And I'll keep doing it until the length of the pendulum is such that when I pull the pendulum back, it hits the wall at the same time the ball hits the ground. Then I can do 100 swings of the pendulum and I'll know the time it takes to hit the wall. And I'll know the acceleration due to gravity. So a very beautiful experiment using the pendulum. Once we knew the pendulum, we then said we have a standard of length. If your pendulum goes back and forth in 1 second, we will call that 1 meter. And everybody now knew what a meter was. Once you have a standard length for commerce, you can then have a standard volume. 10 centimeters by 10 centimeters by 10 centimeters is now a standard volume, so you know how much ghee you're buying at the store. And then if you have a standard volume, you also have a standard mass. Because if you fill that 10 centimeters, 10 centimeters, 10 centimeters with water, you have 1 kilogram. And now everybody in all the markets all over India are going to know what a kilogram is because of the pendulum. We also find out that when we use the pendulum at different places in the Earth, it doesn't give us the same period. And so we realize the Earth is not round, though it looks very round to me. That's a photograph of the Earth, taken from space, and it looks round, but it's not. The pendulum showed us that it's a little wider at the equator than it is the North-South Pole. And when people found this out, they said, wait, God created an imperfect Earth? That surprises people. Then, if the pendulum swings back and forth and keeps its orientation back and forth relative to the stars, if the Earth rotates, then you will see that it seems to change its orientation. And in fact, the picture at the bottom here is in many science museums. They have these pegs all around, and they pull the pendulum back. And during the day, every 15 minutes, if you wait 15 minutes, it'll knock over the next post. Then another 15 minutes, it'll knock over the next post. As the Earth rotates, and the pendulum keeps going in one direction, but the Earth rotates, it knocks over the pegs. So when Foucault figured this out, he made beautiful invitations, like wedding invitations. And they just said, you are invited to see the Earth turn. And people said, oh, I'm coming to this. And he showed them the pendulum for the first time. Now, we also have this pendulum called Newton's cradle, and it teaches us the principle of conservation momentum. It's a very nice toy. If you've never played with it, it's very addictive. If I take one, and one goes in, then one comes out. If I take two, then two go in and two go out. If I take three, oh wait, three go out. It's so clever. If I take four, then four go out. And it makes a beautiful sound. If I take five, then five go out. And only gifted people can hear that sound. It's quite sweet. Now, when you do that, you prove that momentum must be conserved. The mass times the speed must be the same before and after the collisions. This is a huge thing because in science, very few things in the world stay the same. Momentum stays the same. In physics, we only know 6 or 7 things that always stay the same. Momentum is one of them. But then it turns out that it's a little more complicated. You see, if one goes in, one goes out. If two go in, two go out. So let's say one goes in with speed 10, And then the other one comes out with speed 10. Good. 1 times 10 equals 1 times 10. If 2 go in at speed 10, then 2 times 10 equals 2 times 10. 20 equals 20. That's good. But why can't one go in and 2 come out? Because 1 goes in with 10 and 2 come out with 5. 1 times 10 equals 2 times 5. So we have to, I can't get it to do it, but if we all think hard and think 2 come out, and really focus on this. No. And no matter how long you try, this is a game people used to play in the 1700s. This is a fun game. And no matter how many times you try it, 2 will never come out. And if it never happens, then nature is telling us something. When we expect something to happen and it doesn't happen, nature is saying, there's something else you should know about. And in fact, in this case, it was that there's something called kinetic energy. And it's not just the mv has to equal the mv, the mass times speed. It's the 1/2 mv squared. The mass times the v must equal the mass times the v times v. And that only works when 2 go in and 2 go out, or 1 goes in and 1 go out, and does not work when 1 goes in and 2 goes out. And so the pendulum helps us understand that. Then we have Isaac Newton. Isaac Newton said, building on Galileo, that there must be a force on the planets which hold them in orbit around the sun. And Newton was not the first one. Other people were thinking along the same lines. These planets are all held together somehow. Then Newton, though, went further. He said, the apple falls to the earth. The same force that holds the moon to the earth holds the apple to the earth. So just like the moon falls down, the apple falls down, the moon falls down. He said, but the moon doesn't fall down. He said, it does. It just doesn't appear that way. And then, again, where's Newton's genius? It's okay for moons and planets and the sun to have this force. Maybe even okay for an apple. But then Newton said, oh, an apple and an apple attract one another. But you can't measure it, and you can't see it. But that's the way the world should be, as Galileo taught us to do. Apples should attract apples. But you've never seen 2 apples on the table move toward each other. Newton said, it's too small, you'll never be able to see it. But then, 50 years after he died, Cavendish made a pendulum. And Cavendish's pendulum was a torsional pendulum. It was a thin wire, and then instead of swinging back and forth, he had a rod coming out, and the rod could swing back and forth like this. And so he had an apple on each end, and then he put another mass here and another mass there, and the mass is attracted and it shifted. Not very much. That's why when we do it now, we have a laser and a light source and a mirror. But it did move like a pendulum. And Cavendish was able to prove that Newton was correct, but also he was able to determine the density of the Earth. 5.5 times the density of water. We now know, because of this, what's inside the Earth, even though we can't go there. And this is the way we measure the density of all planets. So, the dot would be impressed. The pendulum, acceleration due to gravity, and a standard for length, volume, mass, dazzling. The shape of the Earth, the rotation of the Earth, complex. The conservation of momentum, the conservation of energy, compelling. And the density of the Earth, profound. And so we could end it here. But there's so much more. So much more. So Galileo had this idea, he had the law of chords, this idea of how much time it will take for the pendulum to go down if we start the pendulum at position A and it has to swing down to G. What if we do it at B and it swings down to G? What should it be? And it turned out that the times were not the same. And Galileo was aware of that, but again, he was looking for a perfect world. and it didn't work. The period of the pendulum is not independent of the amplitude. When you pull it back, it takes more time than when you have a small angle. Christian Huygens comes to the rescue. Christian Huygens says, cycloids. This will be the key. So here's a cycloid. If you take a marker and put it at the end of a wheel, and you map out the wheel like this, what will happen is you'll get a shape called a cycloid. It's not a circle, it's a cycloid. And if you take that shape and you turn it upside down, like the black line here, and you make tracks, and we have a line, that's one way to get from the top to the bottom. A parabola is another way, a circle is another way, a cycloid is another way, and there are other ways to do it also. No matter which path you come up with, and yours path can have hills and valleys, whatever you want to do, the cycloid is going to win the race. If all of those balls, the red one, the yellow one, the green one, the black one, the blue one, they all start at the same point at the top, and you can see in the race, the cycloid's already winning. The cycloid always wins the race. It does more than that. It also turns out that when you roll a ball down a cycloid, it doesn't matter where you start it. It takes the same amount of time to come to the bottom. So the purple one starts all the way at the top now. The red one starts right at the bottom, but they got to the bottom at the same time. They all get to the bottom at the same time. That's another property of the cycloid. So what you do, what Huygens realized was, if you put these cycloid cheeks at the top of a pendulum, then it will be independent of the angle. So what's interesting, one of the things that's interesting about this is, when do we abstract, when do we correct? Galileo made incredible advances because he said, it's probably the same. If it wasn't the same, and he said it's not the same, he might have been stuck. But Huygens comes along and says, no, it's not the same, but we can now build on that. And so this, to me, is what I struggle with in my life all the time. When do I look for the simple solution? When do I look for the complex solution? As Kahneman and Tversky won the Nobel Prize, slow thinking, fast thinking. When do we use our fast thinking, which we need to get by and everything? And when do we have to slow down your thinking because it's more complicated? But if you always slow down your thinking, you won't be able to get from here to the other side of the room. So this is called a ballistic pendulum. If I want to measure the speed of something that goes very, very fast, like a bullet, how can I measure it? If it goes across the room, the stopwatch, it's not going to work. So what we do is we take the bullet and we shoot it into a pendulum. And when it hits the pendulum swings. And by measuring how much it swings, using the conservation of momentum and the conservation of energy, we can determine the speed of the bullet. Now, great use of the pendulum. I used to do this in class. I used to do this with an arrow. I would shoot the arrow into the box. Now, the box was not way down there. It was right here. I didn't want to miss. So I would shoot the arrow into the box, and the arrow would get embedded in the box, and the box would shift, and we'd measure how far it goes up. And every year we would do this, and there's a second way to measure the speed of an arrow. You can say that the amount of force it takes to pull back on the bow gives you, and the distance, gives you the kinetic energy or the speed of the arrow. So we used to pull back the bow with the spring scale and measure the force, the distance, and then we determine the speed of the arrow. And almost always we would get 42 meters per second, about 80 miles an hour, 110 kilometers per hour for the speed of the arrow one way, and the other way, instead of 40 meters per second, we get 38 meters per second, or 39 and 42. But there were two numbers that were very accurate, very close, and we would say, that's the speed. Look at two different ways, and it works. One year I did this, and we got 40 2 meters per second and 17 meters per second. And I had to find out where's the mistake. We made a mistake. I know we made a mistake. And I said, measure the mass of the arrow again. Let's measure the angle here. Let's measure the mass of the box. And we kept doing it, and we couldn't find the mistake. And my students just said, it's okay, don't worry about it. It's okay. But it wasn't okay. I was really troubled. And I think for them, this habit of mind we communicate to our students, I know they don't care about the speed of the arrow, but they're watching me saying, he really cares whether these two numbers are the same. And that's the habit of mind you communicate as a teacher. Does this matter to you? Why does it matter to you? So let's take a look at this now. If we were to plot, make a graph of the back and forth motion over time, and we said, well, where is it? What angle is it at? It would make this beautiful cosine curve or sine curve. And we say, oh, cosine curves, I heard of them in math, but I didn't know they had to do with real objects. That's the period of a pendulum, the position versus the time. It also turns out that if we take a spring and we attach a mass, and the mass goes back and forth, back and forth, back and forth, that's also going to be the same graph. So mathematically, this pendulum going back and forth and this spring going back and forth can be described exactly the same. We can go one step further. Oh, we call that simple harmonic motion. We can go one step further. If we take a circle and the circle moves at a constant speed, and we take a projector and put it here so we can only see the dot, the orange circle, as a shadow on the wall. The orange circle, as the circle goes around and around, the shadow goes up and down, harmonic oscillator. The circle, the spring, the pendulum are all described mathematically exactly the same way. In fact, in the 14th century, somebody said, you know, if you drill a hole through the center of the earth, I wonder what would happen to the mass. And the mass will go down toward the center, will go faster and faster and faster, and slow, and they'll go back and forth. And we now know how to compute that. It would take 84.5 minutes to go back and forth. In fact, it's not only through the center of the earth, where you would melt, but you can draw any chord through the earth. You can draw a tunnel. If we could construct a tunnel through the earth like this, we could go from here to here in 42 minutes one way, 42 minutes back. And in fact, you wouldn't even need brakes on this train, because it would stop here, it would stop on one side, it would speed up, and then it would slow down and stop at the other side, you'd get off. Simple harmonic oscillators. So, but that's not our real world. In our real world, things damp out. There's friction, there's areas, and so the pendulum even slows down, and eventually, even though I want it to go forever, it's going to slow down and slow down and slow down. And so the graph looks like that. But that's okay. We can make art out of that as well. So we can have the pendulum swing this way and this way at the same time with different lengths by having strings attached to the ceiling in certain ways. And when we do that, it's going to swing two different ways, and we'll take a look. And of course, it's going to damp out, which means we'll get closer to the middle. And again, that's a pendulum moving in two dimensions. Now, we can again change the back and forth and front and to and fro motion, and we can get all of these shapes as well. And in fact, if we change when we start it, we can get any of these shapes. So let's take a look at something a little easier for us. How do we push a child on a swing? Well, if the children are on a swing, we have to push them. If they want to go higher and higher, we have to push them at the right time. If they're coming toward us, we don't push them. because that's going to stop them. When they get here, then we push them. So we have to push them at the right time, in the right direction, and the child goes higher and higher. So this is called a forced damped harmonic oscillator. It's a harmonic oscillator that damps out, but you can force it so it doesn't damp out. So this is a model I use to try to explain how do we help teachers get better and better. When do you give them a push? How much of a push do you give them? And how do you do it? So you get sluggish, you stop learning, so you need a push. How often, how much? It's like medicine dosage. How much, how often do you do this for optimal things? So I had just come up with this metaphor of the forced damped harmonic oscillator for professional development, professional learning of teachers. I was going to give a talk to the college board, and I told my wife what I was doing. And she said, what does this mean? And I explained about the swing. And so she wrote a note to our children. She said, dearest clever children, there's an email. Dad will be talking to a college board committee about teacher development. The point Dad wants to make is that research is needed to determine when and how often teacher development programs should be implemented in order to ensure the endurance of their benefits. The committee consists of experts in reading, literature, history, maybe some science types. Which analogy would be most effective in communicating his point? An adorable child on a swing with a parent pushing, child gleefully demanding more, and higher, higher, or a forced damped harmonic oscillation with graph. Mom. Oh, P.S. The kid will look like you. So my wife helps me, stay in touch. But there is that question of how often the push is, how do we do it? But also, you can push too hard. You can push the wrong time and too hard. And when that happens, you can have other consequences. But here's the pendulum as a metaphor for learning. Just as the pendulum swings back and forth, learning often involves exploring different ideas and approaches before settling on a solution or understanding. The damped harmonic oscillator. Just as the damping force slows down the oscillation of a damped harmonic oscillator, obstacles and challenges can slow down the progress of students as they learn. The forced damped harmonic oscillator, external factors such as classroom instruction or outside resources can influence the learning process. Those last three metaphors, I didn't write those. Oh, in fact, nobody wrote those. That was artificial intelligence. That was ChatGPT wrote those. Just so you know what's on the horizon for us. It was released six weeks ago. It writes essays for you. When you have the forced damped harmonic oscillator, if you push at the right time, what will eventually happen is you can actually, here's a speaker next to a wine. Some of you have done this with a wine glass. Woo! If you drive that tone, you can actually make the wine glass shatter. And here's a bridge, a big bridge they built in the 1930s. And it wasn't a hurricane, it wasn't a tornado. It was a slight wind at just the right frequency. And the bridge started oscillating. It had been open less than a week. That's steel. And then the bridge collapsed. 3 years building a bridge, 1 week it collapses because they didn't do that. And here's an artist communicating the forced damped harmonic oscillator as a metaphor. So within this frame, I'll read it, you can do this. Within the frame of this broken mirror, we find ourselves in the Germany of the 1930s. A voluminous singer of Wagnerian proportions is blasting her high-pitched voice into her surroundings, creating vibrations that cause crystal goblets to shatter. In this case, the image hints at the so-called Kristallnacht, where Jews were beaten and killed by organized thugs all over Germany. Shortly after this incident, Hitler's Autobahn, convulsed by marching boots, rumbling through the earth, leading straight into the hell of World War II, the destruction of cities and millions of lives. Some, like Einstein, managed to escape and were able to reach a boat to safety. The innocent little girl is swinging happily to new heights, creating good vibrations, but they cannot compete with the poisonous ones that ruled the world. Oh, that's something. So we could end it here, but there is still so much more. Science and engineering. A colleague of mine showed me this swing. Her friend had spent months building a swing, months building it, and was so proud of it, and then hung it up, and it didn't work. And the friend said, "Why doesn't my swing work?" Do you see why it shouldn't work? Well, let me give you a hint. The left side has a long pendulum. The right side has a short pendulum. So it's not going to swing back and forth as one might hope it would. It's going to twist, and it's not going to be a good slide. I was over at Azim Premji University, where they have beautiful artwork, and they have a swing like this in one of the pictures. Artistic license. So we ask students, can you help this person out? How do you fix the swing? And so there's the tree, and you can change it so it does work well. Science is creating new knowledge. Engineering is applying that knowledge to reach a solution. And now we're trying to integrate in our classes science, technology, engineering, math, and all these things. There's also chaos. You've heard of this, these oscillations, the butterfly effect. A small oscillation in Mumbai can create a hurricane system a week later in Bangalore. How is that possible? But all our models say, no, small variations and oscillations will drive bigger changes later on. We also have molecules as oscillators. So here's carbon monoxide. Now, the carbon and the oxygen are not held together with a spring, but they're held together with something that acts like a spring. Then we have a quantum oscillator where the electron goes back and forth in the box, and it oscillates back and forth like the spring, but it's never in the middle. And that's our best model for this, the quantum oscillator. And Daniel Hillis, who's become famous for inventing supercomputers which can do things in a trillionth of a second, 10 to the minus 16 seconds, he has decided that we need to slow down. And so he set for himself to build a clock, a pendulum, that will last 10,000 years. He wants to have a pendulum that will last 10,000 years, and every day a chime will ring, but since there are 10 different bells, it will never repeat over the 10,000 years. Now, it's very hard to find mechanical pieces that won't get corrupted in 10,000 years. And so he has to work on that. You know, things rust, you can't put it in a building. No building lasts 10,000 years. So he put it in a mountain, because the mountain will. So this is his idea, pendulum nowadays. So, this was beauty of pendulum, analysis. They can both be present, and I hope that you now walk away thinking about the pendulum as dazzling, mysterious, complex, profound, and compelling. William Blake said, we're thinking about pendulum, but same, to see a world in a grain of sand and a heaven in a wildflower, hold infinity in the palm of your hand and eternity in an hour. Thank you.